Hello everybody, Tabisomi Taza here, back with another exciting integral calculus lesson. Right, today we'll be looking at lesson 4, or this is the fourth lesson in integral calculus. Today I want us to discuss the fundamental theory of calculus and how we use it to find the area under given figures, given functions, given curves, and so on. It's very nice and easy to find an area of that figure there. If you are given the length, you are given the breadth, no problems. Find the area contained in there. That is just going to be your L times B, and that is your area. No worries. It's nice and easy again. If you are given a figure like that, you know your triangle and your area is going to be half base multiplied by the height h. But now, what if you are asked to find an area under a graph? So here's a graph, here's a trend or a curve that you are given. I'm just going to draw, just making this up really. Okay, here's a curve there, and you are asked to find, let's say, the area between that x value there, let's call it x1, and that x value there, let's call it x2. So I want to find the area under this curve here. Now you might think that that's a triangle, but it's not, because remember, this is a curve. This is constantly changing. The slope of the curve as a particle is accelerating through this is constantly changing, or it's constantly changing direction vectorially. Okay, now finding this area underneath here, you can imagine how daunting it would be if you were to do your length times breadth. Then you will only be able to capture um, or your half breadth times height, I beg your pardon, you'll only be able to capture your half breadth times height. Because if I magnify this, because a curve would be something like that, if we used a triangle, triangle will only be able to give us the tangential information. We can try and sneak in some known figures there to get our curve right down to the T there. But to be honest, there are some points that we are still going to miss. That area there, that area which is not, that area there which is not, that area there which is not a figure that we can take the area of using our known length times breadth or half base times height. The other thing we will need to do then, or the other thing we can do, is you can subdivide these into smaller squares such that you are able to find the area of those squares and you add them together. Once you've done that, you subdivide the ones that you can't find as well, and so on, and so on, and so on, and so on. Concept of pi, okay? Think of the concept of pi. I'll explain it to you some other time, how pi came about and why we use pi for finding the area of a circle, of a curved circle. I digress. We come back to this problem in particular. The theorem, the fundamental theorem of calculus, helps us to solve problems like these, because the fundamental theorem of calculus tells us that the rate of change of the area under the curve is equals to the change in y. In other words, it's equals to y. So in other words, look, if I want to find this area here, this is my y value at this point, and this is my y value at this point. If you consider these two pens that I have, as my x moves towards, my x1 moves towards x2, what's happening to the y values? X1 is moving towards x2, the y values are getting closer and closer and closer. So the rate of change of my x, or the area under the graph, the rate of change of the area under the graph is then getting closer and closer and closer to the value of y, the rate of change of area under the graph with respect to x. In other words, rate of change of area dA dx is equals to y. The rate of change of area under the graph with respect to x is equals to the y value, that y value there. If we do some fancy mathematics there, I can then, multiplying by both sides by dx, get this is equals to y dx. Again, if I do some fancy mathematics there, as we've seen that we add all those little squares and cubes and and whatever in that very not so nice area, I'm using an old English symbol for s, which is sum. We replace now this Greek symbol here when we do integral calculus with with the symbol sum for s. But again, wanting to be even more fancier, we use the old symbol s, old English symbol s, to define an integral there. So the derivative, the rate of change of area is equals to the integral y dx. Now we want a specific area because this will give us all the area under the graph, all the area under the graph. Okay, so we define our boundaries. Our first boundary is x, so we want to find the area between x1 and x2. So at the top we've got x2, which is the upper boundary. At the bottom we put x1, which is the lower boundary. I'm going to keep quiet for a second. I'm going to let you look at it because that is what is called the fundamental theory of calculus. Just like we've been doing before, we can find an arbitrary equation that gives us the general area under a curve for any curve, or we can find specific numbers, or we can find a specific area in square units. Remember the units for area in square units, if we are given the boundaries. Okay, so the next exercises that we are going to do, the next few exercises that we are going to do are going to be just that. How do we use this fundamental theorem of calculus to find those areas, right? Page 189, exercise 6b. Find the following indefinite integrals. Indefinite integrals. I will explain definite and indefinite integrals. Number one, find the following indefinite integrals. The integral of 3x squared dx. Find the integral of 3x squared dx. This is indefinite because we don't have boundaries. Okay, beg your pardon. Just realizing that it's invisible. It's indelible ink. That's what it is. Okay, the integral of 3x squared dx. Find the integral of 3x squared dx. Okay, right. Let's do that. So to find this integral of 3x squared dx, we know how to integrate by now. We add 1 to the power, we divide by the power. So add 1 to 2 there, that's equals 2. 3x to the power 3 divided by the new power, plus we are integrating, don't forget, plus that arbitrary constant c. This is the indefinite integral. Indefinite because there you have it. Okay, suppose we were given boundaries now. Find the area under the curve 3x squared between x is equals to 1 and x is equals to 3. Argument's sake. Okay, so we found now, we can simplify that to be x cubed plus c. We have found now the function x cubed plus c, which is our indefinite integral. Now suppose that instead of an indefinite integral, we want to find the specific area between, as we said, let's take our boundaries to be 1 and 3, or between 1 and 3, our x1 and x2, or our a and b, as you will see in other textbooks. So we want to find dx. This is equals to square brackets. Now this is application, square brackets, the integral of this, that's gonna be x cubed plus, beg your pardon, it's gonna be x cubed, close your square brackets, because we are wanting now to find the definite integral, because we are given the boundaries. So there's no plus c there. We know exactly which values we want to use. Which values do we want to use? Square brackets, we've integrated it. We've got our function inside the square brackets, and we've got boundaries 3 and 1 there. Now we can go on and substitute those boundaries 3 and 1, and then find that specific area in terms of square units. And doing that, this is equals to the next line. Now x to the power 3, that boundary is 3 there, so we just substitute 3 minus x to the power 3, so we substitute the second boundary, which is 1 to the power 3. 3 to the power 3 is 27. 27 minus 1 is 26 square units. And this, folks, becomes our area quantitatively in square units. So we are looking at 26 square units there, if that was 1 and 3. Just an example. Okay, folks? And there you have it. We've covered two things: definite integrals, indefinite integrals. We've also covered, bonus, the third thing, the fundamental theorem of calculus. Alrighty, folks. Thank you so much for joining me again. I hope to see you next time. Have a good day. Bye.